Hello everybody, my name is Danielle Beigel. Today we are going to be going over problem 2 on homework 2 in the class Transport 2. We have a closed capillary system divided in half, one side filled with H2O and the other side filled with D2O, and they're going to be dispersing together, diffusing together in this closed system. We are given the maximum molar diffusive flux at time equals 0.1 seconds, as well as the molecular weight and density of water and D2O. So problem 2 asks us to make an order of magnitude estimate for the maximum driving force for diffusion at 0.1 seconds, which is the time at which we have the maximum molar diffusive flux. So first of all, let's go ahead and go over the definition of the driving force. The driving force is equal to the change in the mole fraction by the change in position. We use the z-axis, and that is equal to the summation of the mole fraction times the molar diffusive flux of the other component minus the mole fraction of the other component times the molar diffusive flux of the first component divided by the total mole concentration times the Maxwell-Stefan diffusivity. So then we have a couple of assumptions to make right here. We know that the summation of all of the molar diffusive fluxes has to be equal to 0. So we know that JH2O plus the molar diffusive flux of H2O and plus the molar diffusive flux of D2O has to be equal to 0, and that also means that the molar diffusive flux of H2O is equal to the opposite of the molar diffusive flux of D2O. We also know that the mole fraction always has to add up to 1. So since this is a binary system, the mole fraction of H2O plus the mole fraction of D2O is equal to 1, and that also means that the mole fraction of D2O is equal to 1 minus the mole fraction of H2O. Since we know that, let's go ahead and expand our summation equation for the driving force. We'll say H2O is component 1. We know that that is equal to the change in the mole fraction for the change in position. And that is equal to the mole fraction of H2O times the molar diffusive flux of H2O minus the mole fraction of H2O times the molar diffusive flux of H2O over the total molar concentration times the Maxwell-Stefan diffusivity. And then that would be added to the mole fraction of H2O times the molar diffusive flux of D2O minus the mole fraction of D2O times the molar diffusive flux of H2O over the total mole concentration times the Maxwell-Stefan diffusivity. We can see from just the top of this first part that that is going to be equal to 0, and that means that this first part will cancel out, and that just leaves us with this section of the equation. Then we can go ahead and use our assumptions that we made earlier to go ahead and rearrange the equation in terms of just one portion, or one component. So we'll do it in terms of H2O. The mole fraction of H2O times the opposite of the molar diffusive flux of H2O minus the 1 minus the mole fraction of H2O times the molar diffusive flux of H2O over the total molar concentration times the Maxwell-Stefan diffusivity. We can go ahead and reduce that down even further when we pull out, of course, we'll just do some algebra to rearrange. Molar diffusive flux goes in the front, and we end up having a -1 because the mole fractions end up canceling out over the total molar concentration times the Maxwell-Stefan diffusivity. In an ideal system, the Maxwell-Stefan diffusivity is equal to the fixed diffusivity, and that is an estimate that we know for liquids that is equal to 10 to the -9th. So that's what we're going to use in this system, so we will go ahead and also replace that, further simplifying our equation. So the driving force of H2O is equal to the opposite of the molar diffusive flux of H2O over the total mole concentration times fixed diffusivity. Then we're just going to need that total molar concentration, and we know that's equal to the concentration of H2O plus the molar concentration of D2O. And from our previous problem that we solved, we know that that is equal to the density of H2O over 2 times the molecular weight of H2O plus the density of D2O over 2 times the molecular weight of D2O. And when we plug in the numbers for that, that is equal to 5.55 times 10 to the 4th, and that is in terms of moles per meter squared. Since we have that, we can go ahead and plug all the numbers into the equation. The molar diffusive flux of H2O is equal to 2.78 moles per meter squared seconds, and the, as we mentioned before, fixed diffusivity is equal to 10 to the -9th for liquids, which is the situation that we have. So the driving force of H2O is equal to -2.78 moles per meter squared seconds divided by 5.55 times 10 to the 4th moles per meters squared, or meters cubed, excuse me, and times 10 to the -9th. This is equal to -5.009 times 10 to the 4th meters per second. And the original question, if you remember, asks for an order of magnitude estimate for the driving force, and that is this number right here, 10 to the 4th. So the driving force has an order of magnitude of 10 to the 4th. And that is the answer to problem 2. If you have any questions, feel free to leave them in the comments down below, and have a great rest of your day.